Hello and welcome to this lecture. We've been looking at estimating parameters given IIT samples of a distribution, right? The distribution has this can be described using some parameters. It could be, if you take Bernoulli P, it could be the parameter P, or it could be gamma or normal, or any distribution has parameters associated with it. If you imagine that your samples are known to come from a certain distribution, but you don't know the parameters, so they come from that class of distributions, but you don't know the specific parameters, how do you go about estimating parameters of that distribution from the sample? So that's the problem we are looking at. This problem is also called the point estimation problem. Some people refer to it as point estimators and things like that. So in case somebody uses that terminology, don't be surprised by it. Point estimation this is also called point estimation. Okay. So we looked at how to measure the error in estimators, and then we came up with this notion that maybe you're concerned with the probability, since error itself is a random variable, you're concerned with the probability that the error takes large values, probability that absolute value of error is greater than something. And to control that using, say, Chebyshev's inequality or something, we are able to see that things like the expected value of the error, the variance of the error matter. Okay, so in this lecture, it's going to be largely equation oriented lecture. We will define these three aspects of a point estimator, which are very crucial and often repeated in analysis: bias, variance and risk of an estimator. So these are all related to the expected values of various quantities, and you will see they have very simple intuitive definitions and they have a nice relationship between them, which we can look at. Okay, of course the moderate skill that you need is, given a description of the estimator, how do you compute bias, how do you compute variance, how do you compute risk? That involves a little bit of manipulation, and I will focus a little bit on that skill as well. Okay, so let's get started. So let's do a quick recap of what mean and variance are. So if you take a random variable x taking values in some set, and then there is a PMF for this random variable. I'm assuming the random variable is discrete. If it is continuous, you will have a PDF. Okay, so the equations are largely the same, but I'm just describing it for discrete for convenience. Okay, so the mean or expected value of x is the summation over every value that the random variable takes, x times the PMF. We know this definition, it's called average value. We'll also denote it by mu in many cases. There's something called the second moment. Second moment is denoted expected value of x squared, right? So the square of x. So it's simply again summation over every value that the random variable takes, but x squared times the PMF. Okay. So now remember, if it were continuous, right? So if it were a continuous random variable with PDF fx of x, then what happens? Summation becomes integral, right? Okay, so this is expected value of x. Let me just write it cleanly. Expected value of x becomes this, and expected value of x squared is going to be integral over of x squared fx of x dx, right? So these two are, the summation gets replaced by integration in the continuous case with the PDF. So I'm simply writing the discrete case. You can imagine what the continuous case will be. A very important quantity is something called the variance, which measures the spread of the random variable about the mean. It's the expectation of x minus mu whole squared. You can also write it as an integral or a summation if you like, but there's this very interesting relationship between the first moment, the mean, and the second moment and the variance. Okay, so what is that relationship? That's given by this. The variance of x is expected value of x. Okay, so there is this huge mistake here. Apologize for that. I should have noted this down. This is wrong. Okay, how do I correct it? So this should go outside. Okay, so it's expected value of x squared minus, apologies for that, it's expected value of x squared minus the expected value of x the whole square, right? So minus mu squared. You can rearrange this. So the second moment is the variance plus square of the mean. Okay, so that's a good formula to remember in your head. If you don't like equations, you want it in words, the second moment is equal to the variance plus the square of the mean. Square of the mean plus the variance is the second moment. Okay. Remember, the mean could be positive or negative, but both the second moment and the variance are going to be positive quantities. Okay, so this is an important result to know. Okay. So we know mean captures sort of like the central value of the distribution, and the variance captures how much do you expect the values of the random variable to be spread about the mean. Okay, so this is a good intuition to remember. Okay, so if you have low variance for a random variable, then most of its values are around the mean. Okay, so this one slide, you already know this, but I'm just doing a quick recap so that when I make comments on this in the rest of the lecture, you'll remember what I mean. Okay, so this mean variance for a random variable, and second moment, of course. Okay, so we're now ready to define the bias of an estimator. Okay, so once again, you have n IID samples according to a distribution x, which is described by some unknown parameter theta. An estimator for theta, we know already, is a function from the samples to the real line. Okay, so we've been denoting it theta hat. Okay, so theta hat of x1 to xn, or simply theta hat in short. So you have an estimator, you have a parameter, and then you have a distribution in terms of the parameter, and you have n IID samples. Okay, so bias of the estimator for a parameter theta is simply expected value of theta hat minus theta. Okay, so this is called the bias of an estimator. We will denote it bias of theta hat comma theta. Maybe you can just write b of theta hat comma theta, so it's clear enough what the bias is. It's the difference between the expected value of the estimator and theta. Okay, so notice theta is a constant, so you can pull the expected value inside and it's a linear term, right? So you have expected value of theta hat minus expected value of theta, and theta is a constant, so you simply get minus theta. Okay, so this is the bias, and you can see this difference in the second form brings out gives you some clarity. Okay, the average value of the estimator. Okay, remember the estimator itself is a random variable. If you do different samplings, you will get different values for the estimator, while theta remains a constant. Okay, theta is an unknown constant parameter, and every time you do sampling, you may get a different value for theta hat. You of course expect the theta hat to be close to theta most of the time, but when you vary the samples, theta hat will vary. It's a random quantity. Okay, so now if you do expected value of theta hat minus theta, what are you saying? You're trying to see the difference between the average value of your theta hat as it varies and the value that you're expecting theta hat to measure, right? So theta hat minus theta, expected value of theta hat minus theta gives you some sort of a difference on average. Okay, so the bias is the expected value of the error. That's the other thing to keep in mind, right? Theta hat minus theta was the error, and error is something which we want to control the distribution of, and bias is the expected value of the error. Okay, so there's another definition of an unbiased estimator. When do you say an estimator is unbiased? If its bias equals 0. Okay, on average, if the estimator is going to be equal to, the expected value of the estimator is going to be exactly equal to the unknown parameter theta, then you say the estimator is unbiased. Okay, so these are all new terminology. So this lecture is going to be full of such kind of terminology. Quite intuitive, simple, but sometimes equations are a little bit unsettling. So take your time, look at the equations closely, you'll see what I mean. Okay, so bias is the expected value of the error. You can also think of it as expected value of the estimator minus the actual parameter. Okay, and if bias is 0, we say the estimator is unbiased. Okay, so clearly from our discussion in the previous lecture, you can see it's good to have an unbiased estimator. An unbiased estimator is good, or at least the bias should be very, very, very small. It should be going to 0 with more and more samples at least, right? So it should have small bias. Estimators should have small bias. If on average you're not going to go to the value that you're trying to estimate, then maybe you're not doing something that's very nice, right? So this is a good parameter of an estimator to keep track of. Okay, so this is important, bias of an estimator. So the next definition is something called risk of an estimator. Okay, so this is also quite important. Particularly, we'll be talking about what's called the squared error risk. That it turns out there are other types of risks for an estimator, and we will talk about the squared error risk. Okay, this is the most standard risk. It's the easiest to understand in some sense. Okay, once again, the setting is the same. Okay, IID samples, n of them from some distribution, parameterized by some unknown theta, and our goal is to come up with an estimator, but then also characterize that estimator. What are the different features of the estimator? We saw already bias is one very useful feature. Now we are talking about risk. Okay, The squared error risk of the estimator theta hat is simply the expected value of theta hat minus theta the whole squared. Okay. So now the bias can be positive or negative. Theta hat minus theta can go, theta hat can differ from theta on the positive side or on the negative side. Even if you take expectation, theta hat, expected value of theta hat might fall on the right of theta or left of theta. So sometimes positive negative is a bit misleading, or doesn't maybe perhaps capture the entire picture. If you may be interested more in the amount by which you differ from theta, and that's where the risk is a very interesting parameter. Whether you deviate on the left side or the right side, the penalty is the same, right? So it doesn't cancel out. Okay, so when you look at expected value of theta hat minus theta, theta hat may be way off to the right of theta for a long time and way off to the left of theta for a long time, and on average this will cancel out and you will get 0. Okay, so even if you have an unbiased estimator, it may be a bad estimator. Okay, so a better way to measure it is using something like risk, which puts a penalty of theta hat minus theta whole squared. So whether you go to the right of theta or to the left of theta, once you square it, you get a large positive quantity and you take the expected value of that. So the risk is small. Okay, you definitely know for sure that your theta hat is around theta. Okay, so most likely to be around theta. So this is the idea behind the risk, and you see why risk is a very, very useful quantity to measure. Okay, on average, being around the theta is important, but you can be far away from the average equally often, and that can cancel out and you can still get a low bias. Okay, so to cover that, one thinks of risk. Okay, risk is clearly a measure of importance here. If the risk is small, you can be sure that theta hat will definitely take values close to theta. You can't go far away because now you're squaring, right? One side, other side won't cancel itself out. Okay, so risk is a very useful quantity as well. Now error is theta hat minus theta. So clearly, so first let me first talk about the second sentence here. Squared error risk is the second moment of error, right? Error is theta hat minus theta. I'm squaring error and I'm taking expected value. So second moment of error is squared error risk. Okay, so that's easy. Another useful terminology is something called mean squared error. Why is this? Because you're squaring the error and then taking the mean expected value. So this quantity, the squared error risk, is also called as MSE, mean squared error, in many situations. Okay, so the same quantity, so many different names. Why? Because it's very, very useful. Okay, so this is a very central quantity and really captures the essence of how well an estimator is working, and so that's why it's used in so many different contexts by so many different people. They all call it different names, but they mean the same thing. Okay, so that's risk for you, risk of theta hat, theta squared error risk, very, very useful quantity. So we've already seen two very interesting quantities relating to quantifying or measuring how good an estimator is. One is the bias. It seems good, but then you can have large bias in either direction, cancelling it out on average. So you look at the squared error, and that is going to really give you a true picture of whether or not things are working well. Okay, so risk is a good quantity. We'll see how to compute these in various examples. Like I said, a very important skill is given a description of the estimator. How do you compute its risk? How do you compute its bias? Right. So using probability and various distributions and various results that we know about probability, you should be able to compute it. That skill is also an important skill to have. We'll come to it soon enough, but let's do one more definition, right? Something that we know already, but we'll look at the connections between these three, and then we'll proceed to the calculation. Okay, then the third definition is variance of an estimator. Okay, now here's an estimator. Now variance of the estimator we know already, right? Any random variable has a variance, and that is simply expected value of the random variable minus its mean whole squared, right? So that's variance. Okay, now what does variance by itself capture, right? So if your estimator has very large variance, what does that mean? As if you give it different sets of samples, the value you're estimating keeps varying a lot, right? That's what variance means. So that's not a desirable property for an estimator, right? So you want an estimator, even if you take one samples, if you take another set of samples, if you take another set of samples, you want the estimator to give values that are close by. Okay, whether the theta hat is close to theta or not is an error thing, but whether or not you're making an error, you don't want the theta hat to vary too much, right? If theta hat is varying all over the place, there is no way you can control the error, right? Wherever theta is, there'll be an error. Okay, So variance of the estimator is also a very important parameter for estimation. Okay, you want your estimator to have low variance. As the samples vary, you want to keep predicting the same thing as long as the distribution is the same. Okay, so variance is a very important parameter, and there is a small difference here. I want you to look at the subtle difference. It's very simple, but still pay attention to this detail here. We are defining variance of the estimator. Okay, so expected value of theta hat minus expected value of theta hat whole squared. What about variance of the error? So if you look at Chebyshev and all that, variance of the error is important. We looked at first moment of the error, that is where bias came from. We looked at second moment of the error, that's the risk. What about variance of the error? Why am I saying suddenly variance of the estimator? Why not variance of the error? So it turns out these two are one and the same. Okay, so error is simply a translated version of the estimator. Okay, so theta hat is your estimator. Error is theta hat minus theta. I'm just translating it by a constant theta. Okay, so when your theta is a constant, theta hat minus theta or theta hat, both of them will have the same variance. Okay, because one is simply a translated version of the other. So variance of error, variance of theta hat, both are the same. Okay, you don't have to bother with that subtle difference between the two. Okay, once again let me summarize. There are three interesting parameters here: bias, which is expected value of the error; risk, which is the second moment of the error; and finally variance of the estimator, and which is also the variance of the error. All these guys you want them to be small. Okay, but there is a very interesting relationship between the three of them, which is famously called the bias-variance tradeoff and all these kind of things. I don't know, so far we haven't seen where the tradeoff is. Forget about where the tradeoff is, but at least there is a bias-variance relationship, bias-variance risk relationship. This is a very important and easy relationship to have. The risk equals bias square plus variance. Okay, so this is the important relationship. You can expand it out if you like. You will see this expansion. Hopefully I have not made a mistake. So proof is actually very, very simple. Risk is the expected value of error squared. That's the second moment of error, and that we know already. Second moment of any random variable is mean of the random variable square plus variance of the random variable. And variance of error, variance of estimator, both are the same. So you just get this relationship. It's a very simple and easy relationship. So this equation is nice and intuitive because it shows ultimately you are interested in the mean square error of your estimator. If you want to keep the mean square error small, you have to keep the bias small. Remember, bias square is positive, variance is positive. So the mean square error is the sum of two positive quantities, bias square plus variance. So if I want to keep the mean square error small, then my bias has to be small and my variance has to be small. Okay, and there could be a trade-off between these two. I may be able to decrease bias, maybe I might increase variance in that fashion, or maybe I want to balance it out so that I get the minimum. Okay, so it's quite often that trade-off happens. Maybe we'll illustrate it with one example. We'll see. Okay, so this is a very nice and interesting relationship. So quite often when you design an estimator, this gives you very useful intuitive ideas. Okay, for more complicated settings, when you don't know how to think of an estimator, first thing you try is to reduce bias. Okay, so this is at least I've used it when I've had to find estimators. You first try to reduce bias. Okay, if you reduce bias, it looks logical that risk may go down, but it turns out sometimes the things you do to reduce bias can increase variance. Okay, it may seem all over the place right now, but just focus on this relationship, right? If you just keep decreasing bias, your variance may blow up. If you just keep decreasing variance, your bias may blow up. So you have to sort of balance between these two. So in many cases, this trade-off is very useful, but this relationship is very, very nice. So you want to keep bias low, variance low as much as possible. Okay, useful relationship. We've seen a whole bunch of relationships. So what we're going to see in the rest of this lecture is how to calculate these things in simple settings. Okay, so we'll once again focus mostly on simple settings and work out, given the estimator, how do you go about computing it. Okay, so let's get started with those examples. That's a useful skill to know. You have to put pen to paper, work it out, get to the answer. Okay, some of you enjoy that, some of you I know get scared of that, but it's an important skill to pick up, right? So let's work on it. Okay, so first is the simplest of examples. We're going to see our three different estimators for the Bernoulli P samples, right? So we had Bernoulli P samples, three different estimators for it. We'll try and compute bias, variance, risk for all the three estimators. Okay, not too difficult, but let's start out. The first estimator was a constant. We didn't bother about the samples. We just said p hat is equal to half, right? So that was our first estimator. Bias is very, very easy here, right? Theta hat minus, so it's half minus p. Variance is 0. Why? Because my estimator is a constant. The expect variance of a constant is 0. So risk simply becomes bias square, which is half minus p whole square. Variance is 0. Is that okay? So easy enough calculation. Make sure you understood how I got it. Bias is expected value of theta hat minus theta, right? Expected value of theta hat minus theta. Now theta hat is a constant here, and this p1 hat equals half. So it just becomes half. Expected value of half is half minus p. Okay, and variance is 0 because variance of half is just 0. There's no variance for a constant, and risk is just bias square plus variance, and so it just becomes bias square. Okay, so easy enough calculation, but it's good to see this and do it a couple of times to be sure. Okay, our next estimators becomes slightly more involved. P2 hat is x1 plus x2 by 2. Bias I am saying is 0. So how do I get this? So I need to expected value of P2 hat, which is expected value of x1 plus x2 by 2. Okay. Remember, this is just a linear function, x1 plus x2, so expected value will go inside and this half will come outside. Half expected value of x1 plus half expected value of x2. What's expected value of x1 and x2? Both of these are just p, right? So Bernoulli p, they are independent, whatever, doesn't matter. Each of them are Bernoulli p. So it's p by 2 plus p by 2 and just becomes p. Okay. So expected value of p2 hat is p. So bias is expected value of p2 hat minus p, and that's 0. Okay. Hopefully you got that. So now variance of p2 hat, okay, I am saying is just see x1 plus x2 by 2, and x1 and x2 are independent now. When you have independent sum of random variables, half, we have a formula for the variance, right? Go back a few lectures to sums of independent random variables and how I found the mean of that, variance of that, you remember? There was a formula that I gave you. You can just blindly apply that formula when you have independent. So it's 1 by 4 variance of x1 plus variance of x2. Okay. What is variance of x1? Each of these guys is p times 1 minus p, right? So that's variance of a Bernoulli p distribution. Okay. So 2p into 1 minus p by 4, that's p into 1 minus p by 2. So risk. Okay. So bias is 0, variance is p times 1 minus p by 2. What is risk? Risk is bias squared plus variance. So that's just 0 plus this guy. So it's p into 1 minus p by 2. Okay. So easy calculations. I mean, you know most of these results. It's easy to just plug in and do it, but just be careful and calmly do it. You'll get to the answer. Okay. So now comes our famous third estimator, which we saw, which we hope is a good estimator. So let's see how to characterize the bias, variance and risk for this estimator. It's x1 plus x2 plus xn divided by n. Bias is going to be 0. Okay, so once again the same calculation as before, the exact same calculation like I did before, except that now you have to use it for n different guys. You can show expected value of p3 hat equals p. Okay, so you just do that. So it's linearity, right? So expected value is going to go inside the summation, and each of these expected values is just p, n of them, so np by n, that's p. Okay, so same calculation as the above case, it will come out. So bias ends up being 0. And for variance, you use the same linear combination of independent random variables. When you do variance, it's just 1 by n squared, sum of the variance. Okay, each of these guys is now p times 1 minus p. So you have np times 1 minus p divided by n. Okay, so this divided by n is very important. So your variance is p times 1 minus p divided by n. Okay, now risk is what? Bias squared plus variance. So it is just 0 plus variance, p into 1 minus p by n. Okay. Now remember, this is falling with n. So risk is falling with n. Okay. So this was an important requirement for us, right? As you get more and more samples, you're expecting your risk to go down. But notice what happens in the p1 hat and p2 hat. There is no n in the picture. Okay. As you get more and more samples, your risk remains the same. So it's not very useful. So you see p3 hat already scores way better than p1 hat and p2 hat. Okay. So for those of you who are worried about p times 1 minus p times 1 minus p, you can argue is less than or equal to 1 by 4. Okay. How do you prove it? You go back to math 1. right? Maximizing a quadratic function. How do you maximize a quadratic function? You'll see that p into 1 minus p lies between 0 and 1, right? So you'll see that at half it achieves the maximum, and that is 1 by 4, okay? So you see why math 1 is useful. All of you keep asking questions about where will I use it, where will I use it? Use it everywhere, okay? So this is less than or equal to 1 by 4. So you see risk is less than or equal to 1 by 4n, so it keeps falling with n. As n increases, the risk keeps falling, okay? So that's a nice thing to see. So 3 different estimators and 3 different risks, and one risk seems to be falling with n, and that's a good quantity to keep in mind, okay? So once again, the skill to focus on here is how to compute the risk and how to compute the bias, how to compute the variance, given an exact description of the estimator and the underlying distribution with the unknown parameter. So this is a good skill to pick up in this lecture. Okay, so what I've done in this plot is just shown you the 3 plots. I'm not going to interpret this plot too much for you. So this is P1 hat, which is, if you remember P1 hat, risk of P1 hat is, half minus P whole squared. P2 hat is P times 1 minus P by 2, right? P3 hat, I think I picked n equals 10 here, so P3 hat is, P times 1 minus P by 10, okay? So you see it looks like this, but, some of you will argue, notice the risk for half minus P squared, just the stupid estimator, it said half, beats even the, the other P3 hat, which we were claiming has a great performance and all that. Risk wise, in this part, this stupid estimator seems way better, okay? But that's only over a small interval, and that's an interesting little thing to worry about. And the other thing to worry about is all of these risks vary with P. They're not staying a constant with P. As P changes, your risk also changes, but we saw how to deal with that, right? You can think of bounding the probability that absolute value of error is greater than P by 10% error or something. You can look at it that way, and that will also work out. So but these plots sort of give you a picture of how to compare different estimators over different ranges of P, okay? And over all the ranges of P, you want your estimator to be better. Just because it's better over a small range, you can't pick it up, okay? And then in the other values, it'll go bad, right? So you can't, this is like saying, I'm really lucky my P is going to be half, so I'll always say half, ignoring the samples. That's not a good idea. You want your estimator to be robust, and as you, whatever P may be, your risk should be low. So that's why the third estimator is a good one. Okay, so this is a simple plot. These kind of plots give you a good picture, a mental picture of what these things are. Okay, so we're going to do a couple of calculations to close out this lecture. Just to get used to the idea of given an estimator, how do we go about calculating bias, variance and risk. Okay, so here's an interesting estimator for a Bernoulli distribution. So notice how this estimator is constructed. I mean, I haven't told you how I came up with this estimator. It is just one estimator. Some of you may not like it, some of you may like it, but anyway, it's a valid estimator, and let's go ahead and calculate bias, variance and risk. So notice what I'm doing here. I'm doing x1 plus x2 plus xn. So this part seems clear, right? So just x1 plus x2 by xn divided by n. This seems clear. But then why am I doing these things? It doesn't seem very reasonable. Okay, I'm adding a root n by 2 and then adding a root n. Okay, so maybe it's reasonable, maybe it's not reasonable. Okay, think about it. But at least it's not a very unreasonable looking estimate. It looks like this x1 plus xn by n, but I've added the square root of n by 2 on the numerator and square root of n in the denominator, just for fun maybe, just to see how bias, variance and risk will behave when such kind of changes are being done. Okay, so let's try bias. For bias, the first step is expected value of p hat, right? All of us know how to do this. Okay, so if you go in with this, each of these, it's a linear operator, so all expected value will go in. Expected value of x1 is just p, so you have np. Okay, so you're going to get np plus root n by 2 by n plus root n. Okay, so that's what you will get. I mean, you can think about how I got this. So the bias is going to be this minus p. Okay, so you will have np plus root n by 2 by n plus root n minus p. Okay, so whatever it's worth, it's if you want, you can go ahead and simplify. Okay, so this np and np will cancel. You will have root n by 2 minus p root n by n plus root n. If you want, you can write it as root n times half minus p by n plus root n. Okay. So the first thing I want to point out is this is not an unbiased estimator. Okay, so this has a bias. It has a non-zero bias, but you know the bias is root n divided by n. Okay, and as n becomes really large, this is going to vanish to 0. Okay, so this will also go to 0. It will keep falling, but except it falls very slow, maybe a little bit more slow than you would want, but it also falls to 0. So it's okay. Bias is going down with n. Okay, it's decreasing with n, but it's not quite 0. Okay, so that's one observation. The next thing is variance. Okay, so variance is not too bad because you know you can ignore the constant, right? This root n by 2 by that by 2 you can ignore because it's only an addition of a constant, doesn't change variance. Only you have to worry only about the sum, and this is again an independent sum. So you'll simply get 1 plus n by root n whole square times variance of each of these guys, and that's just np times 1 minus p, isn't it? So this is the variance. Okay. So once again, remember how I got here. This root n by 2 plays no role in the variance. Okay, you can just drop it, and variance of p hat is equal to the variance of just this first part alone, x1 plus x1 divided by n plus root n. Instead of dividing by n, I am dividing by n plus root n. So I'll get 1 by n plus root n whole square times variance will go inside because x1 to xn are independent, and variance of x1 plus so on till variance of xn, each of them is p times 1 minus p, so np into 1 minus p. Okay, so think about how I got it. I think this is a good exercise for you to get your hands on. Okay, now risk. Okay, it's going to be what? Bias squared n half minus p whole squared divided by, okay, hope I got it right, root n whole squared plus, you know, this is bias squared, right? Bias squared plus the variance np times 1 minus p divided by n plus root n whole squared, right? So this is just variance. This is bias squared. Okay. So let's just add these two guys. So it's n by n plus root n whole squared times half minus p whole square. So that's 1 by 4 minus p plus p squared, and this is p into 1 minus p, that's plus p minus p squared. Okay. So some magic has happened here. Notice these things cancel, and the risk is just n by 4 times n plus root n whole squared. Okay. So it seems almost magical, right? At least the first time I saw this estimator, I felt there was some magic going on. Look at this estimator, its risk. Okay, so the previous 3 estimators we saw, when we plotted it versus p, there was a change, right? There was some dependence on p. The risk of this estimator is independent of p. It's just p has just disappeared. Okay, isn't that interesting? I mean, I always found that a bit intriguing about how this estimator comes about. You might want to think about it, but anyway, that's not the point of this exercise. The point of this exercise is, given any modified estimator like this, right, small changes to this, that, the bias may change, the variance may change, the underlying principles are just the same. It's just, you know, IID samples, and you're combining them to find the estimator. So you have to be able to find the bias, you have to be able to find the variance, and you have to be able to find the risk. Okay, it will involve some algebra, it will involve careful understanding of the probability. It is important, you have to do it, and when you do it, you get final answers. And this particular estimator is a reasonably famous estimator in this area, and it has this wonderful property that its risk is flat across p. Whatever your p may be, the risk is the same. Okay, and that may be desirable in some situations, right? I don't want my risk to change at all, whatever the p may be. It's an interesting thing for you to think about. Okay, so that's one problem. I think with that, we're going to stop this lecture. So hopefully you understood the 3 important characteristics of a point estimator: bias, variance, risk, and there's a simple relationship between them. And given a description of a point estimator, you should be able to put pen to paper and compute its bias, variance, and risk. That's a good skill to pick up. That concludes this lecture. Thank you very much.